This is a rational functions question from the 2011 summer paper 1. It was problem 11, so further maths. The curve C has the equation y equals x squared plus lambda x minus 6 lambda squared divided by x plus 3. And lambda is some constant such that lambda does not equal 1 and lambda does not equal negative 3 divided by 2. Part I says find dy over dx and deduce that if C has two stationary points, then negative 3 over 2 is less than lambda less than 1. No problem. So we can find dy over dx just by using the quotient rule. So dy over dx is equal to 2x plus lambda. Remember, lambda is a constant, so don't worry about that. Don't worry about the minus 6 lambda squared, times x plus 3, and then minus the derivative of x plus 3, which is actually just 1. So minus x squared plus lambda x minus 6 lambda squared. And the whole thing divided by x plus 3 squared. So that's our dy over dx. Now we need to find when it has stationary points. So stationary points is when it's equal to 0. In other words, the top part needs to equal 0. So let's go ahead and expand out the top part. So we get 2x squared plus 6 plus lambda. Well, let's just say 6x plus lambda x for now. And then plus 3 lambda. And then minus x squared minus lambda x plus 6 times lambda squared. So we need this thing to equal 0. And we can combine like terms. So we have x squared and we have a plus lambda x and a minus lambda x here. So we've already taken care of the x squareds as well. So just x squared plus 6x, and then the constant is plus 3 lambda plus 6 lambda squared. And so that needs to equal 0 if there are stationary points. And there are 2 stationary points if delta is greater than 0, because then there would be 2 values of x which solve this equation. So we have that our discriminant delta is equal to 36 minus 4 times 1 times this thing, so 4 times 3 lambda plus 6 lambda squared, and this needs to be greater than or equal to 0. No, it needs to be strictly greater than 0, because we want 2 solutions. And we can divide everything by 4. Well, we can move to the other side and then divide everything by 4, so we have 9 is greater than 3 lambda plus 6 lambda squared, and then rearranging that, it's just 6 lambda squared plus 3 lambda minus 9 needs to be less than 0. And this is nice and easy. If we solve 6 lambda squared plus 3 lambda minus 9 equals 0, we get lambda equals 1 or negative 1.5. And if we draw the parabola, so let's just, we haven't used y, so let's use y. If we draw the parabola y equals 6 lambda squared plus 3 lambda minus 9, we know that it looks like this. So it intercepts the x-axis, or the lambda axes at 1 or negative 1.5, and our parabola looks like this. And so clearly the values of lambda, where it's less than 0, are between negative 1.5 and 1. So negative 1.5 is less than lambda is less than 1. And I believe, yeah, we were supposed to show it was between negative 3 over 2 and 1. Alright, the second part says find the equations of the asymptotes of the curve C. Okay, let's take care of part II here. So we're looking for the equations of the asymptotes of this. Clearly there is a vertical asymptote when x is equal to negative 3. So that one was nice and easy. And to find the equation of the asymptote, which looks like it's going to be oblique, we can simply use polynomial division. So x plus 3 into x squared plus lambda x minus 6 lambda squared. And so we multiply by x, that gives us x squared plus 3x. And then we do our subtraction, lambda minus 3, lots of x. And then we still have minus 6 lambda squared over here. And then to get the lambda minus 3x, we need to multiply by lambda minus 3. And that gives us lambda minus 3x. Plus 3 times lambda minus 3. And then we can do our subtraction to get minus 6 lambda squared minus 3 times lambda minus 3 as our remainder term. But in particular, this is going to be our oblique asymptote. Because writing this function in another way, after we do our polynomial division, we have that y is actually equal to x plus lambda minus 3 plus, and then this remainder. So negative 6 lambda squared minus 3 times lambda minus 3 divided by x plus 3. So as we let x tends to infinity, this part tends towards 0, and so the curve y tends towards x plus lambda minus 3. So our oblique asymptote is x plus lambda minus 3. Alright, part 3 is a little bit of a tough question, not because it's difficult to solve per se, it's just difficult to know how much detail they really want you to go into. It's only worth 3 marks, so probably not too much detail. And we calculated earlier that for lambda between negative 3 over 2 and 1, there's going to be 2 stationary points. But we end up with this quadratic here, and we have lambda here as a constant. It's not really that easy to get an idea of exactly where the values of x would be, especially because lambda can be anywhere between 0 and 1. So I think just near enough is fine, as long as we realize that there's going to be a maximum and a minimum and get them approximately where they should be. And also I believe we proved earlier that functions of the form y equals ax squared plus bx plus c divided by x plus d cannot intercept with their oblique asymptote. And you can just use polynomial division to find the oblique asymptote and then see what happens if you set them equal to one another. I should say simplified rational functions of that form. So this thing isn't going to intercept with its oblique asymptote. Anyway, let's get to work on this thing. So I've set up a little bit of information here about this function. So obviously we also have the vertical asymptote at x equals negative 3. We also know that the y-intercept is negative 6 lambda squared divided by 3. So that will be y equals negative 2 lambda squared. So it can, well, it can be as close to 0 as we like, but it still has to be negative. And if we want to find x-intercepts, then we need to solve the equation x squared plus lambda x minus 6 lambda squared equals 0. And using the quadratic formula, we would get x is equal to negative lambda plus or minus the square roots of lambda squared minus 4 times 1 times negative 6, so plus 24 lambda squared divided by 2. And so it's negative lambda plus or minus 5 lambda divided by 2. So that is equal to 2 lambda or negative 3 lambda. So we do have two x-intercepts. One of them is positive and one of them is negative. Alright, so I think we're pretty much ready to draw this thing now. And I'm just going to imagine that lambda is pretty much 1, just to make this slightly easier. So that means the oblique asymptote is going to be approximately x minus 2. But don't let it be exactly 1 in the drawing, otherwise, I don't know, might somehow lose a mark there. So it should go through. Alright, there we go. So this is our oblique asymptote y equals x plus lambda minus 3. And then we also have the vertical asymptote x equals negative 3, so negative 1, negative 2, negative 3. Alright, so x equals negative 3. Alright, and then we have our two x-intercepts. X equals 2 lambda or negative 3 lambda, so just before negative 3 and just before 2, but it can't intercept the asymptote, so be careful with that. And we have our y-intercept, well, just before negative 2, when we can't intercept with the asymptote, so again, be careful with that. And then so, yeah, then the minimum must be somewhere around here. So that gives us a way to draw this thing. Careful. Oh. Well, I messed that up. Let me do it in parts. Okay, got that part done. Okay, minimum somewhere around there. Cut our y-axis. Cut our x-axis. And then we tend towards the oblique asymptote as x tends towards infinity. And then the other situation must be something like this, because again we can't intersect. It's terrible. Because again we can't intersect with our oblique asymptote or our vertical asymptote, so it forces the shape to take on this form. Alright. And if we look at the marking schedule for that question so far, it just says have the right axes and asymptotes, have the upper branch with its minimum below the x-axis, which we did, and then the lower branch should have had the maximum, local maximum. So yeah, those were the 3 marks came from. So don't spend too much time on a question like that that's only worth 3 marks. Calculating exactly where everything is. Usually if they want you to do a lot of working like that, it's going to be worth more marks, and it might say something like labeling the key points on the graph. Okay, so that's part 3 done. Let's go ahead and check out part 4. It says, draw a sketch of C for the case where lambda is bigger than 3. Okay? Okay, so this time we want to sketch the same curve, but lambda is bigger than 3. And we worked out earlier that there are no stationary points when lambda is bigger than 3. because, well, because of the discriminant thing. Okay, we still have the vertical asymptote at x equals -3, and we still have the x and y intercepts the same. And it still cannot intercept its oblique asymptote. Okay, now this time, let's just imagine lambda to be like 4 or something. So that means that our oblique asymptote is approximately y equals x plus 1. So I guess well, that'll do. The point is the y-intercept of the oblique asymptote should be above 0. Okay, so this is y equals x plus lambda minus 3. Alright, so we still have, so let's, I don't know, that can be about -1/2, so -1, -2, -3. So we still have that vertical asymptote, x equals -3. Goodness me, what a wonky vertical asymptote. Hopefully yours is better. So x equals -3. Okay. Okay, now looking at this y-intercept and these x-intercepts, the y-intercept is going to be really negative this time. So -2 times lambda squared. Well, lambda is some number that's bigger than 3. So it's going to be bigger than -18. So our y-intercept, let's just say, is way down here. And we're going to have two x-intercepts. One of them is going to be bigger than 6. So let's say, I don't know, over here. And then the other one is going to be smaller than -9. So let's say over here. Maybe a little bit further. I don't know, there. It's going to be hard to draw it then. So actually, I'm just going to make it here. Yeah, it's going to be hard to draw this thing. But yeah, just from looking at where these intercepts are and the fact that it cannot intercept its oblique asymptote and obviously it can't intercept its vertical asymptote, we immediately know the shape of the graph. Let me make this a little bit longer to see if I can get my point across when I draw it more easily. So yeah, this side has to be, I guess, this shape here, and then we should get closer and closer to our oblique asymptote as we go further along. Again, I didn't really get my point across, so I'm gonna bring myself closer to the curve, but in reality I should. Yeah, so it's gonna look more like that, where it tends towards the oblique asymptote in that direction, and it tends towards the vertical asymptote in this direction. And the same thing going on down here. We're gonna be tending towards the vertical asymptote as x tends towards -3, and then we're gonna be tending towards the oblique asymptote as x tends towards infinity. It should have really more of. Let me try that again. I didn't choose my scale appropriately, really. But yeah, as long as you can show that it's tending towards the vertical asymptote here and the oblique asymptote here, that's the main point. And just looking at the marking schedule for that, for lambda greater than 3, we need the axes and asymptotes, which means we need the oblique asymptote to have a positive y-intercept. And we needed the left-hand branch and the right-hand branch. So I think we get 1 mark each, as long as the general shape is pretty much correct. It doesn't say anything about intercepts, so I think I got away with reducing my intercepts and messing with the scale a little bit to get the point across about the behavior of each of those two branches. And then it says deduct 1 mark overall for the wrong forms at infinity. So I think by that it meant like if you do something where it like curves around or something like that, then that's definitely wrong. You would lose a mark there. Basically, you're supposed to be showing that it tends towards the asymptotes. I'm not really sure if I showed that clearly enough here. I guess it's potential to lose 1 mark, but it's probably fine. Okay, so that's all for that question.